So the title is this one, but in fact there will be, oh sorry, I have to thank the organizers first. So it was a very a pleasure to attend this conference and to help a bit as I could in the organization. So please ask me again. So there will be 3 stories in this talk. The first part will be some just basic stuff about infinite dimensional geometry. Because I think that infinite dimensional geometry is in fact the common language we have together. So it's good to go back to what we know and what are the model spaces we can use to do geometry in infinite dimension. What are the tools from functional analysis we have? What are the toys we can play with? That means what are the geometric structures that we can play with? And also what are the traps of the infinite dimensional geometry? The second part, which will be a very short story in the middle, because I will recall everything before. I think everyone in this room will be able to understand, even if you don't know what a Poisson bracket is yet, you will understand this trap. It's a very simple trap in infinite dimensional geometry that we discover this summer. But this should be known for a long time. And the last part of it will be more related with shape comparison and shape analysis with curve and surfaces. So let me start with the part 1, model. What are the model spaces that we can use to do infinite dimensional geometry? So there is the first simple model space we can use is a Hilbert space. So I recall what it is. It is a complete vector space with a distance given by an inner product, which is a symmetric bilinear positive definite map on the Hilbert space. And by Risk theorem, we have that the dual of the Hilbert space is itself. Then we can use Banach spaces, which are a generalization of Hilbert spaces. So Banach space is a complete vector space for the distance given by a norm, and a norm should satisfy the triangular inequality, absolute homogeneity, and it should be positive definite. And again, if we take the dual of the Banach space, it's a Banach space again. Then we can generalize a bit to Fréchet setting. So Fréchet space is a complete Hausdorff vector space for the distance given by a countable family of seminorms. In the norm, in the definition of the norm, we assume the last point, which is that it should be definite. If you drop this point, you will end up with a seminorm. And that's what is usually used for the definition of Fréchet space. And if you have a countable family, and this is important, a countable family of seminorms, you can, just by adding them with a right coefficient of a convergence theory, you can end up with a distance. Then you can ask yourself what the dual space of a Fréchet space is. Usually it's not a Fréchet space anymore, but it's a locally convex space. The bidual of it, so if you take twice the continuous dual, is again a Fréchet space. So you can enlarge the model space to include locally convex spaces, and the definition is a Hausdorff topological vector space whose topology is given by a possibly non-countable family of seminorms. And in the non-countable case, it's not a metrizable space anymore. Let me give you some references for infinite dimensional geometry. Klingenberg, the book with title Riemmannian Geometry, the book, Lang's book, Differential and Riemmannian Manifold, Fundamentals of Differential Geometry. In the Frechet setting, the beautiful paper, The Inverse Function Theorem of Nash-Moser by Hamilton. And in the more general setting of locally convex spaces, the book of Kriegel and Micho, Convenient Setting of Global Analysis. So now, what are the tools from functional analysis? Let me just recall some of these theorems that you surely know. In the setting of a complete metric space, so with a distance, you have the Banach-Picard fixed point theorem, which says that if you have a contraction of the space, and if the space is complete for the metric, then you have a unique fixed point. And moreover, this fixed point can be constructed as a limit of sequences if you start with any point of your metric space, and just by this recurrence formula. Then we have the Hahn-Banach theorem. So in the more general context of locally convex spaces, if you have a convex set inside your space, I recall E is completely here. You have a complex set inside and a point which is not in the closure of this set. Then you can, then there exists a continuous functional on the locally convex space, which separates the point and the convex, and the convex set. The third ingredient from functional analysis is the open mapping theorem, which is valid in Frechet setting or in more general setting with webbed locally convex spaces, but I don't want to enter this. So the theorem says that if you have a continuous linear and surjective map from, let's say, two Frechet spaces, then it is open. And in particular, if it's a bijection, then its inverse is also continuous. And the last tool from functional analysis is an inverse function theorem, which is well known, I think, in the Banach setting. So if you have, the theorem, you know, is just saying that if a nonlinear map between Banach spaces has its differential invertible at one point, then it is in fact invertible in a neighborhood of the point. This is not true like this in the Frechet setting. And the famous control example is the exponential map from the set of smooth vector fields on the sphere, on the circle. So the Lie algebra, the group of diffeomorphism of the circle, inside the group of, so let me say again, the exponential map from the Frechet Lie group diff of S1, which is not locally onto. And you know that in this case, the differential is just the identity. So, but there is a version of this inverse function theorem in the setting of Frechet spaces, and there you have to add some condition, just because of this contour example with the Lie algebra of the group of diffeomorphism. And so the conditions are that the nonlinear map from your two Frechet spaces has to be smooth and tame. And I really don't want to explain what tame means. This is really technical. And yeah, doesn't mean anything here. So, but in this case, if you have a smooth tame map, and you have that the derivative, so the equation dfxh equal to k has a unique solution, and the family of inverses that you can get like this is also a smooth tame map, then f is also locally invertible, and each local inverse is a smooth tame map. So yeah, so you can look at the paper of Hamilton where this theorem is proved if you want to know more about it. So let me just recall what we have seen. So the fixed point theorem is valid in the Hilbert setting, Banach setting, Fréchet setting, not in the locally convex setting because it's not a metric space in general. The open mapping theorem is valid everywhere if you have the right condition. And Banach theorem is valid everywhere. And inverse functions theorem, if you add the Nash-Moser version of it, you can have it in Hilbert, Banach, and Fréchet setting. In locally convex spaces, I don't know. There's no theorem as far as I know. So now what are the toys we can play with? The first one is a Riemmannian metric, which is a smoothly varying inner product on a manifold. And you can have strong Riemmannian metric where the metric allowed to identify the tangent space and the cotangent space. But usually in the Banach setting and Fréchet setting and so on, you only have a weak Riemannian metric. And there, be careful, the Levi-Civita connection may not exist for a weak Riemannian metric. Inside the Riemannian setting, the symplectic setting is a generalization in some sense of the Riemannian setting. And just recall what a symplectic form is. It's a smoothly varying skew-symmetric bilinear form that is closed and non-degenerate. And again, you have strong symplectic form where you have identification with tangent spaces and cotangent spaces by the use of this bilinear form. And usually you only have weak symplectic form, where this the symplectic form, the bilinear form, gives you only an injection from the tangent space to its dual. And again, be careful. Darboux theorem, if you know it, does not hold for a weak symplectic form. Why did I say Riemannian is included in symplectic? So this is just Hamiltonian mechanics. So here you have, if you start with a strong Riemannian manifold, so you have identification of tangent space, of the tangent space and its dual by this metric, using this metric. Then you can define the kinetic energy, which is called Hamiltonian in this case, and which I write like a function on the cotangent space. And so the identification using the metric between tangent and cotangent space are called musical isomorphism. So there is a sharp there, and the Hamiltonian take a covector and map it to the metric applied to the vector associated to this covector. In this setting, the cotangent space of the manifold is a strong symplectic manifold, and the symplectic form is the canonical one, which is just defined like this. So you have the projection of the cotangent space on the base, the canonical projection, and the symplectic form is defined like the differential of the Liouville-1 form, which is like this. You have a tangent vector x at x eta. X eta is an element of the cotangent space. And you map this x into R by applying eta to the projection on the base of x. So this is really a natural construction. And then if you look at the flow of Hamiltonian vector, of the Hamiltonian vector field related to this Hamiltonian function, then you end up with the geodesic flow from the metric. So just a remark here. There was a talk yesterday by Maxime Louis, who used the Hamiltonian framework to do parallel transport. And he said that his algorithm doesn't work if you don't take a geodesic. Well, that's the reason. The Hamiltonian framework just see the geodesics on the manifold, not any curve. So now, the symplectic framework can be generalized to Poisson geometry, and the Poisson bracket is just a family of bilinear maps. Here, I'll define them on open subset of the manifold, but these maps, they're just satisfying three things: skew symmetry, Jacobi identity, and the Leibniz rule. And if you start with a strong symplectic form, then it defines a Poisson bracket just by the formula that if you plug in the symplectic form the vector fields associated to the differential of your function, this gives you a Poisson bracket. And here you really need that the symplectic form is strong. Well, a trap again, and that's what I will discuss in the second story. A Poisson bracket may not be given by a bivector field. For this Poisson's bracket given by a strong symplectic form, it is a case, but usually it is not. Well, we have examples where it is not. Now, you can add another toys to your set of toys, the complex structure. So this is a smoothly varying endomorphism of the tangent space, which satisfies that the square of this endomorphism is minus identity. And you have integrable complex structure, which are those that gives you a holomorphic atlas on the manifold. And you have those which are formally integrable, which it just defined by the vanishing Nijenhuis tensor, which is a tensor on your manifold. Usually in the finite dimensional case, you have the Neulander-Nierenberg theorem, which says that if you have a formally integrable complex structure, then you have also an holomorphic atlas. And this does not hold anymore in the Banach setting, let's say. Well, now what are the traps of infinite dimensional geometry? So the golden rule in infinite dimensional geometry is never believe anything you have not proved yourself. Because it's very easy to make mistakes. Because we are so used to the finite dimensional setting that we don't even pay attention to what can be the troubles of the infinite dimensional case. So let me just mention that the distant function associated to the Riemannian metric may be the zero function. So this is a well-known example by Micho and Montfort. You have heard about it certainly because in shape analysis, you know this L2 metric, which gives you zero distance, which is absolutely useless for shape comparison. Then the second point is that the Levi-Civita connection may not exist. Hopf-Riemann theorem does not hold in general, so there is a distinction between geodesic completeness and metric completeness. Darboux theorem that gives you the local way of writing symplectic form in a chart does not apply to weak symplectic forms. Formally integrable complex structure does not imply the existence of a holomorphic atlas. And the tangent space, usually we think of it either as a space of velocity of curve on the manifold or as a space of derivation. And these two notions do not coincide anymore even on a Hilbert space. I will show you this in a moment. And the last point, that Poisson bracket may not be given by a bivector field. So this ends up the first story. Okay. So let me start the second story, which will be very short, I think. So you start with a Hilbert space, separable Hilbert space, let's say, and you define the kinetic tangent vector. A kinetic tangent vector to your Hilbert space, it's just an equivalence class of curves. So you just think as kinetic tangent vectors as velocities. So you have a curve on your manifold, and if you look at it in a chart, well, here it's a Hilbert space. So it's really easy, but usually you look at it in a chart and you identify two curves that have the same velocity at this point. But there are also operational tangent vectors, which are derivations. So derivation is a map, a linear map on germs of smooth functions. This is what I have written, like C infinity of x. These are smooth functions at x where you identify two smooth functions that have the same germ. And satisfying the Leibniz rule. So just that if you apply this derivation to a product of functions, then you have the usual Leibniz rule. So let me just recall. I know now what was this blank slide. Okay, that's bad. Sorry. In this blank slide, I wanted to mention this book of Kriegel and Micho. And it's bad that it doesn't appear, but anyway. So that's in this book I learned about operational tangent vectors. This book is 20 years old. It's a huge book, 600 pages, dealing with infinite dimensional geometry on locally convex vector spaces. This is a book that I have avoided for 10 years. And believe me, you don't want to go in this book unless you are forced to do it. because one of the things that they are explaining is that in this larger setting, you can have smooth functions that are not continuous. So if you look at this, you say, no, these guys, they are crazy. I don't want to go into this. But in fact, now 10 years later, I'm saying, I understand. It's just because at this level, you have a distinction between topology, which gives you continuity and continuous functions and so on, and bonology, which is something which is built on bounded sets. So there is the distinction there. And the smoothness is defined using bonology. So I must apologize because I didn't treat this book very well for the last 10 years, and sorry for that. So Kriegel and Michaud, I'm sorry. By the way, these two authors are in Vienna, which is the best place to live, I think. Well, the last part of this blank slide was a paper I wrote with two collaborators on this second story. The first one is Daniel Beltița from Romania, and the second one is Thomas Golinski. So I have the reference at the end of the slides, so you can see it afterwards. But anyway, this is joint work with Daniel and Thomas. But most of it was already in the book of Michaud, so, and Kriegel Michaud. So we didn't add very much, but anyway, it took 20 years. So let me just recall the construction of queer tangent vectors. So these are called queer because they are not kinematic. So they cannot be constructed with curves. And the ingredients here are the following: the Ries theorem that we have recalled, Banach's theorem that we have recalled, and the fact that the set of compact operators is included in the set of bounded operators on a Hilbert space as a closed subspace. By this fact, by Banach theorem, you have the existence of functional on the set of bounded operator, which take the value 1 as the identity and is 0 on the set of compact operators. So we will call it L. There are many, but this one. And we will use it to define a tangent vector to a Hilbert space, which is not the derivative of a curve on the Hilbert space. And the construction is like this. You take this functional L, and you make it act on the second derivative of a function. So it's just L, and you plug in the second derivative of a function. So this gives you something which take smooth function at x and give you a real number. And then by Ries theorem, you can identify the second derivative of a function with an operator. So the second derivative is just a bilinear function. You make a derivation in one direction, x, and then a derivation in another direction, y. So this takes two tangent vectors, and it's bilinear. So you can write it like x scalar product, an operator A applied to y, just by the duality between Hilbert space and its continuous dual. And you end up with an operation tangent vector dx using this linear form applied to the second derivative, which is of order 2. Order 2 because it uses the second derivative of a function and not only the first one. And the proof is very easy. If you know how to differentiate, you will follow this very easily, I think. So we will just try to understand why this operator dx satisfies the Leibniz rule. So we want to compute this operator acting on a product of two functions, f, g. So this is the goal. So you have first to understand what it is to differentiate once. And this is like this. You have f and g, and first you differentiate f, you multiply with g, and then you take f and differentiate g, and you do it another time, and you have the second derivative of x appearing with a product with j at the point, the symmetric part here, and in between you have the first derivative of f and the first derivative of g applied at x and y. Oh, there probably I missed something here. There should be dfx applied to x times djx applied to y plus dfx applied to y. So there is a mistake here. But the crucial point is that you have something which look like df tensor dg. And if you know a bit of, I don't know, this is usually written like this. This is a rank 1 operator. So this is in quantum mechanics. But this is just a tensor product of two elements of a Hilbert space. So this is a rank 1. In particular, it is compact. The point is that it is compact. So in the middle is something which is compact, and if you apply your functional on this, because L is just 0 on the set of compact operators, this middle term vanishes. And what remains are only the term using the second derivative of f, which is the operator dx applied to f, multiplied by g, and the symmetric part of this. So this is exactly the Leibniz rule here. So this example only uses that you can separate the set of compact operators and the identity. So it's work in the infinite dimensional case only. And also it uses, at some point we have made some identification between the Hilbert space and its dual. So that's also used here. Well, then, if you have understood this, you can understood the construction that follows, which is the construction of a Poisson tensor that is not given by a vector field. And so this is just a trick. You start with a Hilbert space, and this queer operational tangent vector we have constructed, where Kriegel and Montfort did it for us, and you add a dimension R. And then you just make the commutator of two derivations. The first one is given by the queer operation tangent vector, and the second one is just the usual derivation on the direction of R, the one-dimensional direction you added. So this goes like this. you define a Poisson bracket like the commutator of derivation, dx here times d over d lambda, which is, lambda is the parameter in the r direction, minus df applied to derivation of f in the direction of lambda, multiplied by dx applied to g. So because it's a commutator of derivation that do not apply on the same variables, this gives you a Poisson bracket, which cannot be represented by vector fields. And if you look at the Hamiltonian vector field associated to the function minus lambda, lambda is just the parameter in R, then you end up with a queer operational vector field we have constructed before, which involves the second derivative of the function. And that's the end of the story. So I think I have to mention that you can find in the literature that the Leibniz rule implies the existence of a vector field, but as you see, it's not true, so be careful. Now we go to the third story, which is more related, I think, with people are doing here. Shape spaces, so here a picture of shape spaces, and as you see, there is a fiber bundle that I try to represent. So downstairs are shapes which are not parametrized, and upstairs there are many parametrization of the same shape. So the color here is for the velocity of the parametrization. And so you have this fiber bundle, and we call the pre-shape space the total space of this fibration, and shape space can be defined as one-dimensional immersed submanifold. So in this case, one-dimensional submanifold in R2. Another picture involving surfaces. Here again, so you have this fiber bundle structure. Here there is a deformation of a horse into a cat. In blue, that's the deformation in the shape space. And over there are two passes that project to the same deformation into the shape space, but with different parametrization. And the parametrization is really varying in the fibers. It's not just the bottom parametrization. Well, if you apply a constant diffeomorphism on the bottom line, you will not end up with this one. So there is a time varying diffeomorphism which relates the bottom line to the upper line. So the first thing that we have to mention is that shape spaces are nonlinear manifold. And so this is an experiment I made, taking a ballerina here in one position, and the ballerina in another position, and with two different parameterization, and try to well, so the first line is just the linear interpolation between the parametrization, which, as you see, is very bad here. The second line is when you start with arc length parametrized ballerina here, and here an arc length parametrized ballerina, and you look at the linear interpolation between them. It's a little bit better, but not really. So now I will make the distinction between quotient space and fiber bundle, a section of a fiber bundle. Well, so here you have here there will be a list of groups. The first column will be some elements of one orbit of the group. So for instance, for the group of translation, you have this Liberty statue which is translated, and this gives you an orbit of the group. And for the group of rotation, you have this Liberty statue which is just rotated. So these are elements of the quotient space, but you can think of, well, let me make a picture. So you have this fiber bundle over the base manifold. What we call a section is when you have a map from the base to the total space, which make a bijection between the quotient space and the image of this. So here example of sections. So this means that you single out a preferred element in the orbit. For instance, the centered curve that you have in this orbit, or the curve that is starting at one point, the origin. These are section of your fiber bundle. For the group of rotation, you can, for instance, define a section by aligning the axis of the best approximating ellipse of your shape. This gives you a particular section of your fiber bundle, or you can just start in a horizontal direction. So you align the tangent vector at the starting point with the first axis. Another group, the scaling group. So here are elements of the orbits of the scaling group. You just scale your shape. But you can have a preferred element in this orbit which is of length 1, or you can have a preferred element in this orbit which is the element with enclosed area equal to 1. So this gives you two different sections of the same fiber bundle. For the group of reparametrization, so here elements of the orbit are like this. You have different parametrization of the same shape. In the middle, you have arc length parametrization, for instance. So this is one preferred element in the orbit. But you can also take the curvature proportional parametrization here. This is another section. Well, this is just the setting for shapes in the plane. So you have the interval 0, 1, or the circle, and you embed it or you immerse it into R2, and you set you're interested in smooth immersion. So you add the condition that the velocity of your curve is non-zero. So this is an open set in the topology induced by the family of CK norm. So it's a Frechet manifold. And if you add the condition that your curve has length 1, you have a submanifold in this space. And if you add the condition that you want arc length parametrization, so with velocity equal to 1, then you have a subspace in the space of of length 1 curves. Well, in fact, this arc length space, the space of arc length parametrized curves, is a tame C-infinity submanifold of the space of curves. And you can have a definition of the tangent space at a curve gamma. It's just the space of vector field along the curve such that the dot product between the derivative of this vector field and the tangent vector of the curve is 0. So the derivative of the vector field is in the normal direction. This is the tangent space to the arc length manifold, which is the manifold of arc length parametrized curves. This uses the Nash-Mother theorem. You can apply the group of diffeomorphism of your interval du1 on it, which is a Fréchet tame manifold, a tame Fréchet-Lie group, in fact. This was already proved in the Hamilton paper. And you make it act by reparametrization on the group of curve, and this action is tame and a nice Fréchet action. So now, if you take a curve and you reparametrize it by arc length, this operation gives you a map from the fiber bundle on the space, on the section of arc length parametrized curve. So this is really like a projection from the fibers onto the section. So I should write it like this. So in some sense, you contract all the fibers onto your section. And this is a smooth retraction, in fact. And then the theorem we proved with my collaborator Steve Preston is that you have really a diffeomorphic diffeomorphism of Fréchet manifold between arc lengths and this quotient space. This go really nicely. There's no pathology here. By the way, you don't need to add that in this case, so for the interval du1, you don't need to add that you don't need to consider only, well, I have to say, usually this quotient space is a manifold when you restrict yourself to free, how to say, free curves, where the curve where the group of diffeomorphism acts freely. But in this case of 0, 1, it's always a case, because in this case, the group of diffeomorphism fixes 0 and 1, and this this is enough to guarantee that it acts freely. This is in the paper of Mijo, Cervera, so I can give you the reference if you need. Well, then we have two things. We have a quotient space on one side, and we have a manifold, which is a section of the related fiber bundle. On the quotient space, well, there we can have a Riemmannian metric by the usual construction, starting with a Riemmannian metric on the pre-shaped space, which is invariant by the group of diffeomorphism, and going to the quotient. So here I recall the family of elastic metric on the space of curves, which is a two-parameter family with A and B, different coefficient, where A is in the, well, is a metric in the direction of the vector, of the velocity vector field, and B is a coefficient related to the normal direction. So this is a well-known elastic metric introduced by Mio, Srivastava, and so on. And since the group of reparametrization acts in an invariant way on this metric go to the quotient. So here the definition of the quotient metric, it's defined on orbits, and you have to take the infimum of the metric where you take the representative of your tangent vector to the orbit, and you add an element in well, tangent to the orbit of the curve gamma. Well, so this is the last line. I think it's a beautiful picture, because that's exactly what it's supposed to be. And in fact, this is generated by the code which are available online, which are the code from Anush Srivastava and his collaborators, so using the QMAP. So here you plug in the first shape and the end shape, and it gives you the geodesic in the quotient space, so in the shape space between these two. Well, I think it's perfect. I was not able to do better than this. And it's very quick. So, well, what I try to do then with my collaborator Steve Preston is to understand what are these parameters A and B for. How long do you have? How many? 5 minutes, okay. Well, okay. So I will just explain the construction we made. So you have a metric on the quotient space, and you have a diffeomorphism with, between this quotient space to a manifold, which is the space of arc-length parametrized curve. You have a metric there. You can pull back it on the space of arc-length parametrized curve. And this is what we did. We just took the quotient metric, and we just we have rewritten it in terms of arc-length parametrized curve. So this goes like this. You define a metric on arc length. So the W here is a tangent vector to the space of arc length parametrized curve, A1. And you define a metric on it like this. Well, you take the orbit of this omega and compute the quotient metric on this. So what it makes actually is that it projects your tangent vector to the horizontal space related to the quotient metric and compute the metric there. So to understand it, we have to understand what the projection onto the horizontal space is. And that's what we did. And it's not so difficult, actually. So the projection of, so I should, again, try to make a picture here. You have the manifold of arc lengths, parametrized curve, and you have a tangent vector there. And the horizontal space of your metric has nothing to do with arc lengths. So it's well, it's transverse to the fibers, but that's the only thing. And then you project your tangent vector to arc length on this horizontal space, and you see what it do. So the difference between the vectors and its projection is something which can be written like this. So if W is the tangent vector to arc length, then the projection is W minus something which is tangent to the fiber, so which can be written like m times v. V is a velocity vector along the curve. And what m should satisfy is this equation, where kappa is the curvature of your curve. And when you have this, well, you can also compute the energy functional, the gradient of this energy functional, and try to make a path threatening on it. And well, it's really not effective. But what we try to understand is the shape of the energy functional. Well, so we start with a very simple example. You take a circle, and you take a curve which goes from the circle to an ellipse, back to the circle, and what we did is to compute the gradient of the metric on it. So here everything is arc length parametrized. Well, and if you make vary the parameter A and B, in fact, it's only the quotient A over B which is important here, and you look at what's happening in the middle of the path, you see something like this. So depending on the value of the parameter, well, the gradient, which is a vector on your curve, a vector field on your curve, is, well, here we don't know really what it should do, but here it's clear here, for instance, that it tends to make your ellipse more round. That's exactly what we are expecting. From this path, we are expecting to go to the constant path, which join the two cycles. So we expect this kind of behavior. But in fact, this happens only with A and B quite large. And in fact, this depends on the eccentricity of the middle ellipse. So here, the same picture you have, but we vary the eccentricity of the middle ellipse of the initial path. Well, if for the first line is for a small value of A over B, and the second path is for a big value of A and B over B. So in the second line, you see that even if the ellipse is really with a big eccentricity, the gradient will tend to make your ellipse more round. That's what you expect. And if you vary the eccentricity, it's exactly always this behavior. But if A over B is small, then well, depending on the eccentricity of the ellipse, this means depending on how far you are to the constant path, well, you may find gradient which do not what you expect, so which will not point in the direction of the constant path. But if the eccentricity is not so big, so if you are already like a circle, near a circle, then it starts to behave as you expect. Well, this I will skip. So here another experiment. It's a stoics example. You start with a cycle, you go to a cycle, and in the middle of the path, you put a shape like this. So in the center, you have a cycle. a circle here. So in this case, you have the constant path from the circle to itself, and you perturb this path in these directions by changing the middle shape. So there is a direction which I would say stretching direction. You just stretch the circle into an ellipse. And there is a direction which I would call bending, which tends to add some corner and go towards a quarrel. Well, add corner at 4 points. So we compare the energy function on this. And you have this kind of picture where if A over B is small, but the two directions are mostly equal. If A over B is big, then there is a preferred direction. But if you compare this with the same, unit, then you see that in fact the first picture is very flat. So there the landscape is very flat. So this is really not good for path threatening. You need a steep landscape to make the algorithm work. Well, I will just mention an idea we had for surfaces. Well, you can ask yourself for surfaces, is there a preferred section? Well, for curve, we have seen that arc length is a natural section of the fiber bundle. Well, for surfaces, what is there a natural section? Well, in fact, there is. Because genus 0 surfaces are Riemann surfaces. And you have the uniformization theorem, which says that they are conformally equivalent to the unit sphere. So there is a conformal map which maps the unit sphere to your shape, the hand in this case. And in fact, this conformal map is quite unique. It is unique up to the action of PSL2C, sorry. So if you fix 3 points, you have uniqueness. So there is a kind of arc length in this context of surfaces, but the problem is that it uses a uniformization theorem. There are algorithms available for this, but computationally it's heavy. So it's we didn't implement them and use them. So we try to avoid this, and so this is a joint work with Alessandria, Mohamed Daoudi, and Anush Srivastava in PAMI, where we use a really simple idea for mathematics. If you have a fiber bundle, and you don't care about moving into the fiber, like for instance, if you have curve and you don't care about translation, then you can define a Riemmannian metric, well, which is degenerate in the direction that you don't want to use. For instance, the elastic metric, because they use a derivative of the functions, they don't feel translation. So they are defined on the space of shapes modulo translation. And here the same idea, you define a pseudometric on the pre-shape space, which is degenerate exactly in the direction of the fibers. So it costs nothing to move along the fibers. Then you end up with a Riemannian metric on the quotient space, which don't feel at all parametrization. It's just costless. So two curves upstairs that project to the same curve downstairs have the same length. For instance, there is an example here. You go from a horse to a cat using different parameterization paths, but it's the same energy. And again, another example. Or if you start with a hand and just perturb the parametrization of a hand, this is costless. And again, if you just take the same shape and just deform the parametrization, this gives you 0 energy in this setting. Well, that's it. Here are some references. Thank you very much.
Questions? From the Alice.
Usually when we have to consider the quotient shape space, as you said, we need to restrict to free immersions. Can you, I didn't really get in what cases we don't have to do that. You said there's...
for open curves.
For any open curves? Even
Yes.
Curves in a...
So yesterday you draw this kind of curve. I don't remember what it was.
Yeah, it's they were open curves in R3.
Yes, yeah. And the question there was a question in the audience: is it in R3 or is it in the plane? And you seem to think that in the plane it's a problem. It's not a problem in this case. It's not a problem because they are open. But if you go to loops, you may have problems. Okay. So the reference is really an old paper from Micho. I never know if I should say Micho or Micho. Anyway, and how? Micho. But I can give you the reference. That's exactly where they, in fact, define the manifold structure on the quotient space in this setting for free loop, for free action.
Thank you.
Other question? Okay, so thank you to Barbara for this presentation.